you have a microscope. Not any ordinary microscope. This is the most powerful instrument ever conceived by the human mind. It can zoom into the fabric of reality itself. You point it at a tiny patch of empty space, and you begin to zoom in. At first, you see nothing remarkable, just empty space. You zoom past the scale of human hair, past the scale of bacteria, past the scale of viruses. Still nothing but emptiness. You keep going. You zoom past the scale of molecules, past the scale of atoms. Now things get interesting. You can see the fuzzy clouds of electrons orbiting nuclei. But you want to go deeper. You zoom past the scale of atomic nuclei, past the scale of protons and neutrons. You enter the world of quarks, tiny, point-like entities flickering in and out of existence within a sea of gluons. This is already 1 billion times smaller than an atom. But you want more. You keep zooming. And now something starts to change. As you push your microscope to smaller and smaller scales, you notice that the energy required to probe these distances keeps climbing. Your microscope needs more and more power. The photons you are using to illuminate what you are looking at are becoming incredibly energetic. You push through 10 to the negative 20 meters, 10 to the negative 25 meters, 10 to the negative 30 meters. The energy is becoming extraordinary. And then, at approximately 10 to the negative 35 meters, something catastrophic happens. The energy concentrated in your observation beam becomes so intense, so unbelievably focused into such a tiny volume of space, that the fabric of space-time itself begins to warp. A black hole forms right where you were trying to look. Your microscope has not revealed what lies at this scale. Instead, it has destroyed the very thing it was trying to observe. The act of looking has created a gravitational prison from which no information can escape. Welcome to the Planck scale. This is the place where physics does not just get strange. This is the place where physics stops working entirely. Every theory humans have ever constructed, every equation we have ever written, every framework we have ever devised to understand reality, all of them shatter into meaningless fragments at this scale. General relativity, the theory that describes gravity and the large-scale structure of the cosmos, breaks down completely. Quantum mechanics, the theory that describes atoms and subatomic particles with breathtaking precision, breaks down completely. The standard model of particle physics, which catalogues every known fundamental particle and 3 of the 4 fundamental forces, breaks down completely. Even our most ambitious attempts at a unified theory, string theory, loop quantum gravity, and others, have not yet conquered this frontier. Today, we are going to take a journey to the absolute bottom of reality. We are going to explore what the Planck scale is, where it comes from, and why it represents the most profound crisis in the history of physics. We are going to understand exactly how and why our best theories fail at this scale. We are going to examine the deepest paradoxes and thought experiments that emerge when quantum mechanics collides with gravity. We are going to survey every major theoretical framework that physicists have proposed to solve this crisis. And we are going to confront what might be the most unsettling possibility of all, that the Planck scale is not just a limit of our current knowledge, but a fundamental boundary of reality itself, beyond which concepts like space, time, distance, and duration simply cease to have any meaning. This is not speculation. This is not science fiction. Every single thing we will discuss today is grounded in real physics, real mathematics, and real research conducted by some of the most brilliant minds in human history. And yet, despite all that brilliance, the Planck scale remains unconquered. It is the Mount Everest of physics, except we are not even sure the summit exists in any conventional sense. So if you are the kind of person who wants to understand the universe at its deepest, most fundamental level, you are in exactly the right place. Make sure you subscribe to this channel and turn on notifications, because content like this, content that goes this deep into the biggest questions in science, is exactly what we do here. Drop a comment right now telling me what you think happens at the smallest scales of the universe. Is space smooth and continuous, like a sheet of glass? Or is it grainy and discrete, like pixels on a screen? I genuinely want to know your intuition on this, because by the end of this video, you might completely change your mind. And hit that like button, because it helps this video reach more curious minds who are hungry for real, deep scientific content. Now, let us begin at the beginning. Not the beginning of the universe, although we will get there. Let us begin with the man whose name is attached to every single unit we will discuss today. Let us begin with Max Planck himself and a discovery he made in 1899 that he could not have possibly understood the full significance of at the time. The year is 1899. Physics is in a strange state of confidence mixed with unease. On the one hand, the classical framework built by Newton, Maxwell, and others seems nearly complete. The laws of mechanics explain the motion of everything from billiard balls to planets. Maxwell's equations unify electricity, magnetism, and light into a single beautiful theory. Thermodynamics and statistical mechanics explain heat, energy, and the behavior of gases. Lord Kelvin, one of the most prominent physicists of the era, famously suggests that physics is essentially finished, that there are only two small clouds on the horizon of an otherwise clear sky. Those two clouds are the puzzling results of the Michelson-Morley experiment, which failed to detect the luminiferous ether, and the problem of blackbody radiation, which classical physics cannot correctly describe. Those two small clouds would turn out to be the seeds of the two greatest revolutions in the history of physics. The Michelson-Morley result would lead Einstein to special relativity and eventually to general relativity, and the blackbody radiation problem would lead Max Planck to quantum mechanics. But neither revolution has happened yet in 1899. Planck is simply a careful, methodical German physicist trying to solve a specific technical problem. The problem is this: when you heat an object, it glows. The hotter it gets, the brighter it glows, and the color of the glow shifts from red to orange to yellow to white to blue. This is blackbody radiation, the electromagnetic radiation emitted by an idealized perfect absorber and emitter of radiation. Classical physics, specifically the Rayleigh-Jeans law, predicts how much energy should be emitted at each wavelength, and the prediction works beautifully for long wavelengths. But at short wavelengths, in the ultraviolet part of the spectrum, the classical prediction goes haywire. It says the object should emit infinite energy at short wavelengths. This is obviously absurd, because real objects do not emit infinite energy. This failure is so dramatic that it earns the name the ultraviolet catastrophe. Planck solves the problem by making what he initially considers a mathematical trick. He assumes that energy is not emitted continuously, but in discrete chunks, in tiny packets that he calls quanta. The size of each energy quantum is proportional to the frequency of the radiation, with a proportionality constant being a new fundamental constant that Planck introduces. This constant, which we now call Planck's constant and denote by the letter h, has a value of approximately 6.626 times 10 to the negative 34 joule seconds. With this assumption, Planck derives a formula for blackbody radiation that matches experimental data perfectly across all wavelengths. The ultraviolet catastrophe is resolved. But here is what makes Planck's contribution to our story today so remarkable. Even before he fully developed his quantum hypothesis, Planck realized something extraordinary about the fundamental constants of nature. He noticed that by combining just three constants, the speed of light c, Newton's gravitational constant g, and his new constant h, or more precisely, the reduced Planck constant h bar, which equals he divided by 2 pi. He could construct quantities with the dimensions of length, time, mass, energy, and temperature. These are not arbitrary human inventions like meters and seconds and kilograms. These are units that emerge naturally from the fundamental constants of the universe itself. Planck recognized this and wrote that these units would retain their meaning for all times and for all civilizations, including extraterrestrial and non-human ones. Planck had discovered what we now call the Planck units, and they define the scale at which all of physics breaks down. Let me take you through each one, because the numbers themselves tell a story that is almost impossible to believe. The Planck length is defined as the square root of h bar times g divided by c cubed. When you plug in the numbers, you get approximately 1.616 times 10 to the negative 35 meters. Let me try to help you grasp how unimaginably small this is. Take a single proton, the nucleus of a hydrogen atom. A proton is already extraordinarily tiny, about 10 to the negative 15 meters across. Now imagine you could expand that proton to the size of the entire observable universe, which is about 93 billion light-years across. In this absurdly magnified picture, the Planck length would still be smaller than a human hair. That is how small the Planck length is. Here is another way to think about it. Suppose you wanted to measure the diameter of a single atom using Planck lengths as your ruler. An atom is about 10 to the negative 10 meters across. The Planck length is about 10 to the negative 35 meters. So you would need about 10 to the 25 Planck lengths to span a single atom. Now suppose you counted off 1 Planck length every second. How long would it take you to count all the way across that atom? It would take you approximately 10 million times the current age of the universe. The atom would be long gone. The stars would have burned out. The universe would be a cold, dark void, and you would still be counting. The Planck time is defined as the square root of h bar times g divided by c to the 5th power. Its value is approximately 5.39, 1 times 10 to the negative 44 seconds. This is the time it takes light to travel 1 Planck length. In 1 single second, there are more Planck times than there have been seconds since the Big Bang. Actually, that vastly understates it. The number of Planck times in 1 second is roughly 10 to the 44. The number of seconds since the Big Bang is roughly 4 times 10 to the 17. So there are about 10 to the 26 times more Planck times in a single second than there have been seconds in the entire history of the universe. The Planck mass might surprise you. It is defined as the square root of h bar times c divided by g, and its value is approximately 2.176 times 10 to the negative 8 kilograms, which is about 22 micrograms. That is roughly the mass of a flea egg or a small grain of sand. This does not sound very impressive until you realize the context. For a fundamental particle, the Planck mass is enormous. A proton has a mass of about 1.7 times 10 to the negative 27 kilograms. The Planck mass is about 10 to the 19 times heavier. If you could somehow concentrate the Planck mass into a single fundamental particle, that particle would have properties that defy everything we currently understand about particle physics. The Planck energy follows directly from the Planck mass through Einstein's famous equation E equals mc squared. It works out to approximately 1.956 times 10 to the 9th joules, or equivalently about 1.22 times 10 to the 28 electron volts. To put this in perspective, the Large Hadron Collider, the most powerful particle accelerator ever built, reaches energies of about 10 to the 13 electron volts. The Planck energy is 10 to the 15 times higher than that. 1,000,000 billion times more energetic than anything we can produce. To build an accelerator that could reach the Planck energy using current technology, you would need a machine roughly the size of the Milky Way galaxy. The Planck temperature is obtained by dividing the Planck energy by Boltzmann's constant. It comes out to approximately 1.416 times 10 to the 32 Kelvin. This is sometimes called absolute hot, the counterpart to absolute zero. For comparison, the core of the Sun is about 15 million Kelvin. The Planck temperature is roughly 10 to the 25 times hotter than the center of the Sun. It is the temperature that prevailed in the universe at the very first instant after the Big Bang, during what physicists call the Planck epoch. Above this temperature, our current theories of physics simply cannot make meaningful predictions. And finally, the Planck density, which is the Planck mass divided by the cube of the Planck length. This gives approximately 5.155 times 10 to the 96 kilograms per cubic meter. This number is so absurdly large that no analogy can truly do it justice. If you took the entire observable universe, all 100 billion galaxies, all the stars, all the planets, all the gas, all the dark matter, everything, and you compressed it all into the volume of a single atomic nucleus, you would still not be anywhere close to the Planck density, not even in the same ballpark. The Planck density exceeds that scenario by many, many orders of magnitude. These numbers are staggering. And they should be, because they represent the absolute limits of our physical theories. But here is the crucial question that elevates the Planck scale from a curiosity to the central problem of physics. Why do these specific combinations of constants define the limits of our knowledge? What is so special about the intersection of C, G, and H bar? The answer lies in what each constant represents. The speed of light, c, is the fundamental constant of special relativity. It defines the maximum speed at which information can travel and sets the relationship between space and time. Newton's gravitational constant, g, is the fundamental constant of gravity. It determines the strength of the gravitational interaction and, in the context of general relativity, it controls how mass and energy curve the fabric of space-time. And Planck's reduced constant, h bar, is the fundamental constant of quantum mechanics. It sets the scale at which quantum effects become important and defines the relationship between the wave-like and particle-like properties of matter and energy. When you combine all three constants into the Planck units, you are creating quantities that sit at the intersection of all three domains simultaneously. The Planck scale is where special relativity, gravity, and quantum mechanics must all be considered at the same time. And that, as we are about to see in extraordinary detail, is precisely where everything falls apart. To understand why everything falls apart at the Planck scale, we first need to understand what works above it. we need to appreciate the three great pillars of modern physics, what each one tells us about reality, where each one succeeds brilliantly, and where each one has a blind spot that becomes fatal at the Planck scale. The first pillar is quantum mechanics. Quantum mechanics is the physics of the very small. It governs the behavior of atoms, electrons, photons, and all subatomic particles. And it is, by some measures, the most successful scientific theory in human history. Its predictions have been verified to extraordinary precision, in some cases matching experimental measurements to 12 decimal places. The anomalous magnetic moment of the electron, for instance, is predicted by quantum electrodynamics, the quantum theory of electromagnetic interactions, and the prediction agrees with experiment to better than 1 part in a trillion. No other theory in any field of science has achieved anything close to this level of accuracy. But quantum mechanics describes a world that is fundamentally different from the world of everyday experience. In the quantum world, particles do not have definite positions or definite velocities until they are measured. Instead, they exist in superpositions of multiple states simultaneously. An electron can be in 2 places at once. A photon can take 2 different paths at the same time. This is not a metaphor or an approximation. It is a literal description of what quantum mechanics tells us about reality at the subatomic scale. The mathematical framework of quantum mechanics revolves around the wave function, a mathematical object that encodes all the information about a quantum system. The wave function does not tell you where a particle is. It tells you the probability of finding the particle in various locations if you look. Before you look, the particle genuinely does not have a definite position. This is the famous measurement problem, and it remains philosophically controversial to this day, but its mathematical and experimental foundations are rock solid. For our story, the most important feature of quantum mechanics is the Heisenberg uncertainty principle. Formulated by Werner Heisenberg in 1927, this principle states that there are pairs of physical quantities that cannot both be measured with arbitrary precision at the same time. The most famous pair is position and momentum. The more precisely you know where a particle is, the less precisely you can know how fast it is moving, and vice versa. Mathematically, the uncertainty in position delta x multiplied by the uncertainty in momentum delta p must be greater than or equal to h bar divided by 2. There is an analogous uncertainty relation between energy and time. The uncertainty in energy delta E multiplied by the uncertainty in time delta t must also be greater than or equal to h bar divided by 2. This means that on very short timescales, the energy of a system can fluctuate wildly. The shorter the time interval you examine, the larger the energy fluctuations can be. This has a profound consequence. On extremely tiny timescales, enough energy can appear from nothing, seemingly violating conservation of energy for a brief instant, to create pairs of particles and antiparticles. These are called virtual particles, and they are not just a theoretical abstraction. Their effects are measurable. The Casimir effect, where 2 metal plates placed very close together in a vacuum experience a tiny attractive force due to virtual particle fluctuations, has been experimentally confirmed. The Lamb shift in the spectrum of hydrogen, caused by virtual particle interactions, has been measured with extraordinary precision. So quantum mechanics tells us that the vacuum of space is not truly empty. It is a seething ocean of virtual particles constantly popping in and out of existence. And the smaller the scale you examine, the more violent these fluctuations become. Remember this. It will become critically important when we reach the Planck scale. The second pillar of modern physics is general relativity. Published by Albert Einstein in 1915, general relativity is the theory of gravity, but it is far more than that. It is a theory of space-time itself. Before Einstein, gravity was understood through Newton's framework. In Newton's picture, gravity is a force that acts instantaneously between any two objects with mass. The Earth pulls on the Moon pulls on the Earth, and this mutual attraction keeps the Moon in orbit. Newton's theory works brilliantly for most everyday purposes. It correctly predicts the orbits of planets, the trajectories of baseballs, and the tides of the ocean. But Einstein realized that Newton's picture has a fundamental flaw. It requires gravity to act instantaneously across any distance, which violates the principle that nothing can travel faster than light. Einstein replaced Newton's picture with something far more profound. In Einstein's framework, gravity is not a force at all. It is the curvature of space-time. Mass and energy tell space-time how to curve. Curved space-time tells matter how to move. The Earth does not pull on the Moon through some mysterious force. Instead, the Earth's mass curves the space-time around it, and the Moon simply follows the straightest possible path through that curved space-time. What we perceive as the force of gravity is actually the geometry of the universe. General relativity has been confirmed by every experimental test it has been subjected to. It correctly predicts the precession of Mercury's orbit, which Newton's theory could not explain. It predicts that light should bend as it passes near massive objects, gravitational lensing, which has been observed countless times. It predicts that time runs slower in stronger gravitational fields, gravitational time dilation, which has been measured with atomic clocks on aeroplanes and is essential for the proper functioning of GPS satellites. It predicts the existence of gravitational waves, ripples in the fabric of space-time produced by accelerating masses, which were directly detected by the LIGO experiment in 2015. And it predicts the existence of black holes, regions of space-time where the curvature becomes so extreme that nothing, not even light, can escape. And the first image of a black hole was captured by the Event Horizon Telescope in 2019. For our story, the key insight from general relativity is the relationship between energy density and space-time curvature. The more mass or energy you concentrate into a given region of space, the more space-time curves in that region. There is a critical threshold, defined by the Schwarzschild radius. If you compress any amount of mass into a sphere with a radius equal to its Schwarzschild radius, which is 2 times g times m divided by c squared, that mass will form a black hole. An event horizon will form, separating the inside of the black hole from the rest of the universe forever. For everyday objects, the Schwarzschild radius is absurdly tiny. For the Earth, it is about 9 millimeters. You would have to compress the entire Earth into a sphere smaller than a marble to create a black hole. For the Sun, the Schwarzschild radius is about 3 kilometers. But for objects with the Planck mass, something remarkable happens. The Schwarzschild radius of the Planck mass turns out to be approximately equal to the Planck length. This is not a coincidence. This is the mathematical signal that gravity and quantum mechanics are on a collision course at the Planck scale. The third pillar is the Standard Model of Particle Physics. This is a quantum field theory framework that describes 3 of the 4 fundamental forces of nature: the electromagnetic force, the weak nuclear force, and the strong nuclear force, along with all known elementary particles. The Standard Model contains 6 quarks, named up, down, charm, strange, top, and bottom. It contains 6 leptons, the electron, muon, tau, and their corresponding neutrinos, It contains the gauge bosons that mediate the forces, the photon for electromagnetism, the W and Z bosons for the weak force, and the gluons for the strong force. And it contains the Higgs boson, discovered at the Large Hadron Collider in 2012, which gives mass to the W and Z bosons and the fermions through the Higgs mechanism. The Standard Model is spectacularly successful within its domain. It predicted the existence of several particles before they were discovered experimentally. It correctly describes the results of every particle physics experiment conducted to date. It is one of the great intellectual achievements of the human species. But the Standard Model has a glaring omission. It does not include gravity. The Standard Model works in flat spacetime, where gravitational effects are negligible. It has no mechanism for incorporating the curvature of spacetime or the dynamics of gravity. If you try to add gravity to the Standard Model using the same quantum field theory techniques that work so brilliantly for the other three forces, you get nonsense. You get infinities that cannot be tamed. The theory becomes non-renormalizable, a technical term that we will explore in depth shortly. So here is the situation. We have three extraordinarily successful theoretical frameworks. Quantum mechanics and its extension, quantum field theory, describe the microscopic world with incredible precision. General relativity describes gravity and the large-scale structure of the cosmos with incredible precision. The Standard Model catalogues all known particles and three of the four forces with incredible precision. Together, they explain virtually everything we observe in the universe. But they cannot all be true everywhere. There are physical situations where you need all three frameworks simultaneously. Situations where quantum effects, gravitational effects, and particle physics all matter at the same time. And in every single one of those situations, our theories produce contradictions, infinities, or outright nonsense. Those situations all involve the Planck scale. And that is where we now turn. Let us now walk carefully through the specific mechanisms by which physics breaks at the Planck scale. This is the heart of our story, and it requires us to understand several distinct but interconnected arguments, each of which demonstrates a different aspect of the breakdown. The first and perhaps most intuitive argument involves the thought experiment I described at the very beginning, the attempt to build a microscope that can see the Planck length. Let us now make this argument rigorous. In order to observe or measure anything at a given scale, you need a probe whose wavelength is comparable to or smaller than the scale you want to resolve. This is why electron microscopes can see smaller things than optical microscopes, because electrons have shorter wavelengths than visible light. To see an atom, you need X-rays or electron beams with wavelengths of about 10 to the negative 10 meters. To see a proton, you need probes with wavelengths of about 10 to the negative 15 meters, which corresponds to the energies produced by large particle accelerators. The relationship between wavelength and energy for a photon is simple. Energy equals h times c divided by wavelength. Shorter wavelengths mean higher energies. Conversely, higher energies mean shorter wavelengths and the ability to resolve smaller distances. Now let us push this to the Planck length. To resolve distances of about 10 to the negative 35 meters, you need a photon, or any probe particle, with a wavelength of about 10 to the negative 35 meters. The energy of such a photon would be h times c divided by 10 to the negative 35 meters, which works out to approximately the Planck energy, about 10 to the 19 giga-electron volts. Here comes the problem. What happens when you concentrate the Planck energy into a region the size of the Planck length? Let us calculate the Schwarzschild radius of this energy. Using E equals mc squared, the equivalent mass is the Planck energy divided by c squared, which is the Planck mass. And the Schwarzschild radius of the Planck mass is 2 times g times the Planck mass divided by c squared. When you compute this, you get approximately the Planck length. This means that the photon you are using to probe the Planck scale has so much energy that when it arrives at the point you are trying to observe, it creates a black hole whose radius is comparable to the very distance you were trying to measure. Your probe has become a trap. The information you were seeking is now hidden behind an event horizon. And it gets worse. If you try to use an even higher energy photon, thinking that more energy will give you better resolution, you make the black hole larger, not smaller. The Schwarzschild radius grows linearly with mass, so doubling the energy doubles the size of the black hole you create. You are now further from seeing the Planck scale than when you started. This is fundamentally different from any other measurement limitation in physics. At larger scales, you can always improve your resolution by using more energy. At the Planck scale, this strategy reverses. More energy means less resolution, not more. There is a minimum observable distance, and it is approximately the Planck length. This argument tells us something profound. The Planck length is not just a very small distance that we happen to lack the technology to probe. It is a fundamental limit imposed by the combined structure of quantum mechanics and general relativity. No conceivable technology, no matter how advanced, can circumvent it. It is as fundamental a barrier as the speed of light. The second argument for why physics breaks at the Planck scale is more technical but equally devastating. It concerns the non-renormalizability of quantum gravity. When physicists develop a quantum field theory, they start by identifying the fundamental fields and particles of the theory and writing down the rules for how they interact. Then they calculate the probabilities of various physical processes, like two particles scattering off each other, by adding up contributions from all possible ways the process could occur, including contributions from virtual particles. The problem is that these calculations almost always produce infinities. Even in the well-understood and experimentally verified theories of quantum electrodynamics and the Standard Model, the raw calculations give infinite answers. This seems catastrophic, but physicists discovered a remarkable procedure called renormalization that allows them to systematically absorb these infinities into a finite number of measurable quantities. Here is the intuitive idea behind renormalization. The infinities arise because the calculations include contributions from virtual particles with arbitrarily high energies, corresponding to arbitrarily short distances. But our theories might not be valid at those extreme scales. Renormalization is essentially a way of saying we do not know what happens at infinitely high energies. So let us parameterize our ignorance with a few measurable quantities and see if the theory still makes predictions. For the electromagnetic force, the weak force, and the strong force, this procedure works brilliantly. You need to measure only a finite number of quantities, the masses and coupling constants of the theory, and then the theory correctly predicts everything else. But when you try to apply this procedure to gravity, it fails completely. The technical reason is related to the dimensionality of Newton's gravitational constant g. In the system of units used by particle physicists, the coupling constant of electromagnetism is dimensionless, just a pure number approximately equal to 1/137. This dimensionlessness is crucial for renormalizability. It means that the strength of the electromagnetic interaction does not change with energy in a way that introduces new types of infinities at each level of approximation. But Newton's constant g has dimensions. In natural units where h bar and c are both equal to 1, g has dimensions of length squared, or equivalently 1 over mass squared. Specifically, g is proportional to 1 over the Planck mass squared. This means that the gravitational coupling strength grows with energy. At low energies, gravity is incredibly weak, which is why quantum gravitational effects are utterly negligible in everyday life and in all current experiments. But at energies approaching the Planck energy, the gravitational coupling becomes of order 1, meaning gravity becomes just as strong as the other forces. The consequences for the calculations are disastrous. When you compute quantum corrections to gravitational processes, each successive order of approximation introduces new types of infinities that require new parameters to absorb. At the first order of approximation, you need to introduce a couple of new parameters. At the second order, you need more. At the third order, even more. And this continues without end. To make the theory fully predictive, you would need to measure infinitely many parameters, which is obviously impossible. The theory has no predictive power at Planck scale energies. It is, in the language of physicists, non-renormalizable. This does not mean that the quantum field theory of gravity is useless. At low energies, far below the Planck scale, it works perfectly well as an effective field theory. You can calculate the quantum corrections to Newtonian gravity, and they give sensible, finite answers. The leading quantum correction to the gravitational potential between two masses was calculated decades ago, and it is extraordinarily tiny, far too small to measure with current technology. But the effective field theory approach explicitly breaks down at the Planck energy. Above that scale, you need a fundamentally different theory, a theory of quantum gravity that does not yet exist in completed form. The third argument involves what John Archibald Wheeler called quantum foam, and it gives us perhaps the most vivid picture of what the Planck scale might actually look like. As we discussed, the energy-time uncertainty principle allows energy fluctuations of magnitude delta E over time intervals of magnitude delta t, with the constraint that delta E times delta t is at least h bar over 2. The shorter the time interval, the larger the energy fluctuation. Now consider what happens at the Planck time scale, approximately 10 to the negative 44 seconds. Over such an incredibly brief interval, the energy fluctuation allowed by the uncertainty principle is approximately the Planck energy, about 10 to the 19 giga-electron volts. And we have already seen that the Planck energy concentrated into a Planck length volume creates a black hole. So at the Planck scale, the quantum vacuum is not just filled with virtual particle-antiparticle pairs, as it is at larger scales. It is filled with virtual black holes. Tiny, ephemeral gravitational singularities pop in and out of existence everywhere, at every point in space, with a frequency of about 10 to the 43 times per second. Part 2. These virtual black holes radically distort the geometry of spacetime at the Planck scale. Each one creates a tiny region of extreme curvature, an event horizon, and possibly even a singularity that lasts for a Planck time before evaporating. The cumulative effect of countless virtual black holes appearing and disappearing everywhere, all the time, is to turn the smooth fabric of spacetime into a chaotic, frothing mess. Wheeler called this quantum foam, and it suggests that at the Planck scale, the smooth, continuous spacetime that general relativity assumes and that we experience in everyday life simply does not exist. Think about the ocean. From an airplane, the ocean's surface looks perfectly smooth and flat. From a boat, you can see waves. From very close up, you can see ripples and spray. And if you could somehow zoom into the surface at the molecular level, you would see individual water molecules bouncing around chaotically, and the very concept of a smooth surface would lose all meaning. The analogy is imperfect, but it captures the essential idea. Space-time may look smooth and continuous at the scales we can observe. But at the Planck scale, that smoothness dissolves into a quantum mechanical chaos that our current theories cannot describe. The fourth argument concerns what is known in the physics community as the problem of time. This is one of the most philosophically profound consequences of the clash between quantum mechanics and general relativity. And it strikes at the very heart of what we mean by physical reality. In quantum mechanics, time plays a very specific role. It is an external parameter, a backdrop against which quantum states evolve. The fundamental equation of quantum mechanics, the Schrödinger equation, tells you how the wave function of a quantum system changes with time. Time ticks along uniformly and externally, providing a fixed stage on which the quantum drama unfolds. Crucially, in quantum mechanics, time is not itself a quantum variable. It is not subject to uncertainty. It is not measured by an operator. It is just there, providing the beat to which the quantum world marches. In general relativity, time plays a completely different role. Time is not an external backdrop. Time is part of the dynamical fabric of space-time. Time can stretch and compress. Time runs slower near massive objects. Time can be warped by gravity. Time is not a fixed stage, it is one of the actors in the play. At the Planck scale, these two incompatible roles of time come into direct conflict. If space-time itself is subject to quantum fluctuations, as the quantum foam picture suggests, then time itself is fluctuating. But quantum mechanics requires a stable, external time parameter to even formulate its equations. How can you write down a Schrödinger equation, which describes how things change with time, if time itself is a quantum variable that does not have a definite value? This is not a minor technical issue. It is a fundamental conceptual crisis. The most ambitious attempt to write down a quantum equation for the entire universe, the Wheeler-DeWitt equation, encounters this problem head-on. When Bryce DeWitt wrote this equation in 1967, following ideas from John Wheeler, he found that the equation contains no time variable at all. The Wheeler-DeWitt equation says that the quantum state of the universe does not change. It simply is. This seems to imply that at the most fundamental level, the universe is timeless. Time, in this picture, is not fundamental. It is an approximation, something that emerges at larger scales from the correlations between different parts of the universe. But that has no meaning at the Planck scale. If this is correct, then our most basic intuitions about reality, that things happen in sequence, that causes precede effects, that the universe has a history, are all approximations that break down at the Planck scale. The flow of time that we experience every moment of our lives might be an illusion created by the macroscopic averaging of a fundamentally timeless quantum reality. The fifth argument involves the singularities predicted by general relativity and their implications for Planck-scale physics. A singularity, in the context of general relativity, is a point where the curvature of spacetime becomes infinite. The theory predicts that singularities form inside black holes and existed at the Big Bang. At a singularity, the mathematical quantities that describe spacetime curvature, density, and temperature all blow up to infinity. But infinity is not a physical quantity. When a theory predicts infinity, it is telling you that it has been pushed beyond its domain of validity. The theory is not describing reality at that point. It is screaming for help. In the 1960s, Roger Penrose and Stephen Hawking proved a series of remarkable theorems showing that singularities are not flaws in particular solutions of general relativity. They are inevitable consequences of the theory's structure. Under very general physical conditions, any sufficiently massive collapsing object will form a singularity. And if you trace the expansion of the universe backward in time, you inevitably encounter a singularity at the Big Bang. These are the Penrose-Hawking singularity theorems, and they tell us that general relativity itself predicts its own failure. And where does that failure occur? At the Planck scale. The singularities predicted by general relativity are points where the density approaches or exceeds the Planck density, where the temperature approaches or exceeds the Planck temperature, and where the curvature of spacetime reaches Planck scale values. The singularities are not just mathematical curiosities, they are signposts pointing to the Planck scale, telling us that a new theory is needed there. Now I want to pause here and make sure you appreciate the magnitude of what we have established so far. We have seen 5 independent arguments, each coming from a different angle, each using different physics, and all converging on the same conclusion. The Planck scale is where our physics breaks. The microscope argument shows that you cannot observe distances shorter than the Planck length without creating black holes. The non-renormalizability argument shows that the quantum field theory of gravity loses all predictive power at the Planck energy. The quantum foam argument shows that space-time itself dissolves into a chaotic froth at the Planck scale. The problem of time shows that the very concept of temporal evolution becomes meaningless at the Planck time. And the singularity theorems show that general relativity itself points to the Planck scale as the place where it needs to be replaced. These are not 5 different problems. They are 5 facets of the same problem. And that problem, the incompatibility of quantum mechanics and general relativity at the Planck scale, is widely regarded as the single most important unsolved problem in all of fundamental physics. Let us now go deeper and explore the paradoxes that emerge from this breakdown. These paradoxes are not just intellectually fascinating. They provide crucial clues about what the correct theory of quantum gravity might look like. The first paradox we need to examine is the hierarchy problem. This is one of the most puzzling features of our universe, and it is directly connected to the Planck scale. Consider the 4 fundamental forces of nature. The strong nuclear force, which holds quarks together inside protons and neutrons, is the strongest. The electromagnetic force, which governs the interactions of charged particles, is about 100 times weaker than the strong force. The weak nuclear force, which is responsible for certain types of radioactive decay, is about 10,000 times weaker than the electromagnetic force. And then there is gravity. Gravity is so much weaker than the other forces that the comparison is almost laughable. The gravitational force between 2 protons is about 10 to the 36 times weaker than the electromagnetic force between them. That is a factor of 1 followed by 36 zeros. This is an absurd disparity. Why is gravity so incredibly, outrageously weak compared to the other forces? In the language of particle physics, this question translates into the hierarchy problem. The strength of gravity is set by the Planck mass, which is about 10 to the 19 gigaelectron volts. The strength of the weak force is set by the electroweak scale, characterized by the mass of the Higgs boson, about 125 gigaelectron volts. The ratio between these 2 scales is about 10 to the 17, which is roughly the square root of the ratio 10 to the 36 that we mentioned earlier for the force strengths. Why is there such an enormous gap between these two fundamental scales of physics? Why is the Higgs mass 10 to the 17 times smaller than the Planck mass? The puzzle becomes even more acute when you consider quantum corrections. In quantum field theory, the mass of the Higgs boson receives contributions from virtual particles of all energies, up to whatever energy scale the theory is valid. If the standard model is valid all the way up to the Planck scale, these virtual particle contributions should drive the Higgs mass up to the Planck mass. The only way to get the observed Higgs mass of 125 giga-electron-volts is if there is an incredibly precise cancellation between the enormous positive contributions and enormous negative contributions, leaving behind a tiny residual. This cancellation must be precise to about 1 part in 10 to the 34. Such extreme fine-tuning seems deeply unnatural and suggests that either there is a new symmetry or mechanism protecting the Higgs mass, which was one of the motivations for supersymmetry, or there is something fundamental that we are missing about the relationship between the Planck scale and the electroweak scale. Despite decades of searching, no new symmetry or mechanism has been found. The Large Hadron Collider was expected by many physicists to discover supersymmetric particles or other new physics that would explain the hierarchy problem. It did not. The Higgs boson was found, exactly as predicted by the standard model, but nothing else. The hierarchy problem remains wide open, and it represents one of the deepest connections between the physics we can observe and the mysterious Planck scale that we cannot. The second paradox is even more dramatic. It is called the cosmological constant problem, and it has been called the worst prediction in the history of physics. In general relativity, the energy density of empty space, the vacuum energy, has gravitational effects. It contributes to the curvature of space-time and affects the expansion rate of the universe. Einstein originally introduced a cosmological constant into his equations to allow for a static universe, then abandoned it when the expansion of the universe was discovered, calling it his greatest blunder. But in the late 1990s, observations of distant supernova revealed that the expansion of the universe is not just continuing, it is accelerating. Something is pushing the universe apart with increasing speed. The simplest explanation is a small, positive cosmological constant, a tiny vacuum energy density that pervades all of space. The observed value of this vacuum energy density is about 10 to the negative 47 giga-electron-volts to the 4th power. In Planck units, this is approximately 10 to the negative 122. It is an extraordinarily tiny number. Now here is the problem. Quantum field theory predicts that the vacuum should have a much, much larger energy density. The virtual particles constantly popping in and out of existence contribute to the vacuum energy. If you add up all the contributions from virtual particles up to the Planck energy, you get a vacuum energy density of approximately 1 in Planck units. Compared to the observed value of 10 to the negative 122 in Planck units, the theoretical prediction is too large by a factor of 10 to the 122. Let that sink in. 10 to the 122. This is not a small discrepancy. This is a number so large that calling it astronomical would be an insult to astronomy. It is 122 orders of magnitude. It represents the most extreme disagreement between theoretical prediction and experimental observation in all of science. Something must be cancelling the enormous vacuum energy predicted by quantum field theory, leaving behind only the tiny residual that we observe. But what? We have no satisfactory answer. Some cancellation mechanism must exist. But its nature remains one of the deepest mysteries in physics. And this mystery is fundamentally a Planck scale mystery, because the enormous vacuum energy prediction comes from virtual particle contributions at all scales up to the Planck scale. The third paradox takes us into the realm of black holes and brings together quantum mechanics and gravity in their most dramatic confrontation. This is the black hole information paradox. In 1974, Stephen Hawking made one of the most remarkable theoretical discoveries of the 20th century. By combining quantum field theory with the curved space-time of general relativity, Hawking showed that black holes are not truly black. They emit radiation. This radiation, now called Hawking radiation, arises from quantum effects near the event horizon. Virtual particle-antiparticle pairs are constantly being created everywhere in space. Near the event horizon of a black hole, it is possible for one particle of the pair to fall into the black hole while the other escapes to infinity. The escaping particle carries away a tiny amount of the black hole's energy, and from a distance, it looks as though the black hole is radiating. The temperature of this radiation is inversely proportional to the mass of the black hole. For a stellar mass black hole, the Hawking temperature is about 10 to the negative 8 Kelvin. Extraordinarily cold and completely unmeasurable with current technology. But for very small black holes, the temperature becomes significant. A black hole with the Planck mass would have a temperature of approximately the Planck temperature, and it would evaporate almost instantaneously. Hawking's discovery has a stunning implication. If a black hole radiates, it loses energy and therefore mass. Over immense timescales, a black hole will shrink and eventually evaporate completely, disappearing in a final burst of radiation. For a stellar mass black hole, this process would take about 10 to the 67 years. For a supermassive black hole, it could take 10 to the 100 years or more. But eventually, every black hole will evaporate. And here is where the paradox strikes. The Hawking radiation appears to be perfectly thermal, meaning it is characterized solely by the temperature and carries no other information. It does not depend on what fell into the black hole. Whether you throw in a book, a piano, or an elephant, the Hawking radiation looks the same. It is just heat radiation. But quantum mechanics has a sacred principle called unitarity, which says that information can never be truly destroyed. The evolution of a quantum system is always reversible in principle. If you know the final state of a system, you should always be able to reconstruct its initial state. This is a fundamental requirement for the mathematical consistency of quantum mechanics. Now, consider the full life cycle of a black hole. Matter with specific, detailed information about its quantum state falls in. The black hole evaporates completely through featureless thermal radiation. At the end, all the matter is gone, the black hole is gone, and only thermal radiation remains. Where did the information go? If the information is truly lost, unitarity is violated, and quantum mechanics is wrong. If the information somehow escapes in the Hawking radiation, then either general relativity is wrong about the nature of event horizons, or there is some incredibly subtle mechanism that encodes the information into the radiation in a way that Hawking's original calculation missed. This paradox has consumed the attention of theoretical physicists for over 50 years. It has generated some of the most creative and controversial ideas in modern physics. The resolution, whatever it turns out to be, almost certainly requires a complete theory of quantum gravity. Because the final stages of black hole evaporation, when the black hole shrinks to the Planck mass and the Planck size, are precisely the regime where both quantum effects and gravitational effects are maximally important. The information paradox is, at its core, a Planck scale problem. In recent years, significant progress has been made on this paradox. Work by researchers including Ahmed Almheri, Netta Engelhardt, Donald Marolf, Henry Maxfield, Jeff Pennington, and others has suggested that the information is indeed preserved and does eventually come out in the Hawking radiation. The key idea involves what are called quantum extremal surfaces and the island formula, which extends the Bekenstein-Hawking entropy formula in a way that accounts for quantum effects. The Page curve, proposed by Don Page in 1993, describes how the entropy of the Hawking radiation should evolve over the lifetime of the black hole if information is preserved, first increasing as radiation is emitted, and then decreasing as the information begins to come out. Recent calculations using the island formula have shown that the Page curve can be reproduced in certain models, suggesting that information is preserved. But the full resolution of the paradox remains incomplete, and it ultimately depends on understanding what happens at the Planck scale near the end of the evaporation process. The fourth paradox brings us to one of the most profound and suggestive results in all of theoretical physics. It connects black holes, information, and the Planck scale in a way that hints at the deep structure of reality. In 1973, Jacob Bekenstein proposed that black holes have entropy. Entropy, in physics, is a measure of the number of microscopic states that correspond to a given macroscopic state. A gas in a box has high entropy because there are many possible arrangements of the gas molecules that all look the same from the outside. A crystal at absolute zero has low entropy because there is essentially only one arrangement. Bekenstein argued that the entropy of a black hole is proportional to the area of its event horizon. Hawking then refined this, arriving at the precise formula. The entropy of a black hole equals the area of its event horizon divided by 4 times the Planck area, where the Planck area is the square of the Planck length. Let me state this more explicitly. If A is the area of the event horizon and LP is the Planck length, then the entropy S equals A divided by 4LP squared. This formula is remarkable for several reasons. First, the entropy is proportional to the area of the event horizon, not its volume. This is deeply counterintuitive. For most physical systems, entropy scales with volume. If you double the volume of a box of gas, you roughly double its entropy. But for black holes, it is the surface area that matters. This is our first hint that in a quantum gravitational context, the amount of information that can be stored in a region of space is not proportional to the volume of that region, but to the area of its boundary. Second, the formula involves the Planck area. This tells us that the fundamental units of black hole entropy, the fundamental bits of information associated with a black hole, are each associated with a patch of the event horizon about 1 Planck area in size. It is as though the event horizon is tiled with tiny Planck area cells, each carrying 1 bit of information. Third, the numbers are staggering. A stellar mass black hole with a mass of about 10 solar masses has an event horizon area of about 10 to the 9 square meters. The Planck area is about 10 to the negative 70 square meters. So the entropy, the number of bits of information, is roughly 10 to the 78. This is far more information than is contained in all the atoms in the observable universe. The Bekenstein-Hawking entropy formula is one of the few results in physics that involves all 3 of the fundamental constants, C, G, and H bar. Simultaneously, it sits at the triple intersection of relativity, gravity, and quantum mechanics. And it contains the Planck length as a fundamental unit of information, suggesting that the Planck scale is not just the scale where physics breaks, but the scale where the true informational nature of reality is encoded. This leads directly to the fifth major insight, the holographic principle. Inspired by the Bekenstein-Hawking entropy formula, Gerard Hooft in 1993 and Leonard Susskind in 1995 proposed that the maximum amount of information that can be stored in any region of space is proportional to the area of the boundary of that region, measured in Planck units, not its volume. This is an astounding claim. It means that in some fundamental sense, the three-dimensional world we experience might be equivalent to two-dimensional information encoded on a surface. The universe might be a hologram, a three-dimensional projection of two-dimensional data written in Planck area pixels on a distant boundary. In 1997, Juan Maldacena provided the most concrete realization of the holographic principle with his anti-de Sitter conformal field theory correspondence, usually called the AD-S-C-Eft correspondence. Maldacena showed that a theory of quantum gravity in a specific curved spacetime called anti-de Sitter space is exactly mathematically equivalent to a non-gravitational quantum field theory living on the boundary of that spacetime. The boundary theory is a perfectly well-defined quantum theory with no gravity. The bulk theory is a full theory of quantum gravity. And they are the same theory, just described in different languages. This suggests something extraordinary about the Planck scale. The breakdown of physics at the Planck scale in the bulk might not be a real breakdown at all. It might be an artifact of trying to describe the universe in terms of bulk spacetime, when the true description is in terms of the boundary theory. The holographic principle suggests that spacetime itself, including the Planck scale physics that seems so intractable, might be a derived concept, an emergent phenomenon that arises from the dynamics of a lower-dimensional, non-gravitational quantum theory. There is a sixth crucial concept that connects directly to the Planck scale and the limits of measurement. It is called the generalized uncertainty principle, or GUP. The ordinary Heisenberg uncertainty principle states that the product of the uncertainty in position and the uncertainty in momentum must be at least h bar over 2. This places a lower limit on how precisely you can simultaneously know both the position and momentum of a particle. But it does not place any lower limit on the precision of a position measurement alone. In principle, according to standard quantum mechanics, you could measure a particle's position with unlimited precision at the cost of complete ignorance about its momentum. But when you include the effects of gravity, this changes dramatically. The gravitational effects modify the uncertainty principle by adding a term that becomes important at very high energies, precisely at the Planck scale. The modified relation, the generalized uncertainty principle, can be written as delta x is greater than or equal to h bar divided by 2 delta plus alpha times the Planck length squared times delta divided by h bar, where alpha is a dimensionless constant of order 1 that depends on the specific model. The first term is the standard quantum uncertainty. It says that to localize a particle more precisely, you need higher momentum, which is just the usual trade-off. The second term is the gravitational correction. It says that at very high momenta, corresponding to very high energies, the uncertainty in position actually starts increasing again. This is because high-energy probes create gravitational distortions that smear out the position measurement. The combined effect of both terms is that there is a minimum possible uncertainty in position. No matter how you adjust the momentum of your probe, you can never achieve a position uncertainty smaller than about the Planck length. This minimum uncertainty arises at a probe momentum of approximately the Planck momentum. The existence of a minimum length has profound implications. If you cannot localize anything more precisely than the Planck length, then distances shorter than the Planck length are not just unmeasurable, they may be physically meaningless. The generalized uncertainty principle suggests that the concept of a point in space, a location with zero size, may not exist in nature. Space itself may have a granular structure, with the Planck length as the fundamental grain size. Now let us turn to the theoretical frameworks that physicists have developed in their attempts to solve the Planck scale crisis. Each of these approaches offers a different vision of what might lie beyond the breakdown of our current theories. Each has achieved remarkable insights, and each faces significant challenges that remain unresolved. The most widely known approach is string theory. The central idea of string theory is deceptively simple. What if the fundamental constituents of nature are not zero-dimensional point particles, but one-dimensional objects, tiny vibrating strings? These strings are incredibly small, with a characteristic length scale close to the Planck length, about 10 to the negative 35 meters. They can be open, with two endpoints, or closed, forming tiny loops. Different vibrational modes of the string correspond to different particles. Just as a violin string can vibrate in its fundamental mode, or in various harmonics, each producing a different musical note, a fundamental string can vibrate in different modes, each corresponding to a different elementary particle with specific properties like mass, charge, and spin. The most remarkable feature of string theory is that one of these vibrational modes naturally corresponds to a massless particle with spin 2. In the language of quantum field theory, a massless spin 2 particle is precisely a graviton, the quantum of the gravitational field. String theory does not have to add gravity by hand. Gravity emerges automatically and inevitably from the vibrational spectrum of the string. This is why string theory is often described as the first framework that naturally unifies quantum mechanics and gravity. How does string theory address the Planck scale breakdown? The key is the finite size of the string. In a conventional quantum field theory based on point particles, two particles can come arbitrarily close together, and it is this possibility of zero-distance interactions that leads to the infinite quantities plaguing quantum gravity. But strings cannot be compressed below their characteristic size. When two strings interact, the interaction is spread out over the length of the string, which smears out the point-like interactions that cause the infinities. String theory provides a natural ultraviolet cutoff at the Planck, or string scale, rendering the gravitational calculations finite without the need for renormalization. String theory also reveals a remarkable property called T-duality that has deep implications for the Planck scale. Consider a string moving in a space that has one direction wrapped into a circle of radius r. It turns out that the physics of a string in this space is completely identical to the physics of a string in a space where the circular direction has radius L squared divided by r, where L is the string length scale. This means that if you try to make the circle smaller than the string length, the physics automatically maps onto a larger circle. There is no way to probe distances smaller than the string length, because the physics below that scale is equivalent to physics above it. The string length, approximately the Planck length, acts as a fundamental minimum distance, not because of any limitation of measurement, but because of a deep symmetry of the theory. However, string theory comes with significant challenges and requirements that have made it controversial. First, Mathematical consistency requires string theory to have extra spatial dimensions beyond the three we observe. The original formulation, called bosonic string theory, requires 25 spatial dimensions. But this version has problems including the prediction of particles with imaginary mass called tachyons. The more physical superstring theories, which incorporate a symmetry called supersymmetry, require 9 spatial dimensions for a total of 10 spacetime dimensions. And the most comprehensive formulation, M-theory proposed by Edward Witten in 1995, requires 10 spatial dimensions for a total of 11 spacetime dimensions. If string theory is correct, the extra dimensions must be hidden from our everyday experience. The standard explanation is that they are compactified, meaning they are curled up into tiny shapes too small for us to detect. The geometry of these compactified dimensions determines the properties of the particles and forces we observe in our 3 large dimensions. A specific shape of the extra dimensions corresponds to a specific vacuum state of the theory, a specific set of particles, forces, and constants of nature. And here lies perhaps the most significant challenge facing string theory. The number of possible shapes for the extra dimensions, and therefore the number of possible vacuum states, is staggeringly large. Current estimates suggest there may be 10 to the 500 or more possible vacua. This enormous collection is called the string theory landscape. Each vacuum in the landscape corresponds to a different possible universe with different particles, forces, and constants. Our universe is presumably one particular vacuum in this landscape, but string theory provides no clear mechanism for predicting which one. This has led to intense debate about the predictive power of string theory. If the theory allows 10 to the 500 possible sets of laws of physics, and we have no way to determine which one corresponds to our universe, has the theory really explained anything? Some physicists argue that the landscape, combined with the eternal inflation scenario in cosmology, leads naturally to a multiverse, in which all possible vacua are realized somewhere, and we simply find ourselves in one that allows complex life to exist. This is the anthropic landscape. Others find this reasoning deeply unsatisfying, and argue that a truly fundamental theory should uniquely determine the laws of physics. As of now, string theory has not produced any predictions that have been confirmed by experiment. The energy scales at which stringy effects would become directly visible are far beyond the reach of any existing or foreseeable particle accelerator. The extra dimensions, supersymmetric particles, and other novel phenomena predicted by various versions of string theory have not been observed. This does not mean string theory is wrong, but it does mean that its status as a physical theory, as opposed to a mathematical framework, remains uncertain. The second major approach to quantum gravity is loop quantum gravity, often abbreviated as LQG. While string theory starts from particle physics and tries to add gravity, loop quantum gravity starts from general relativity and tries to quantize it directly. The two approaches have very different philosophies, and they lead to very different pictures of what the Planck scale looks like. The foundational idea of loop quantum gravity is to take Einstein's insight that gravity is the geometry of spacetime and apply the rules of quantum mechanics directly to that geometry. In general relativity, the fundamental variable is the metric tensor, which describes the shape and curvature of spacetime at every point. Loop quantum gravity reformulates this in terms of new variables, called Ashtekar variables after Abai Ashtekar, who introduced them in 1986, that make the theory look more like a gauge theory, similar to those used in particle physics. When you apply the standard quantization procedure to these variables, something remarkable happens. The operators corresponding to area and volume turn out to have discrete spectra. Just as the energy levels of a hydrogen atom come in discrete steps, the area of a surface and the volume of a region in loop quantum gravity come in discrete quanta. There is a smallest possible area, which is of order the Planck area, and a smallest possible volume, which is of order the Planck volume. This means that in loop quantum gravity, space is not continuous. It is made of tiny discrete chunks. The geometry of space is described by mathematical structures called spin networks, which are graph-like objects consisting of nodes connected by edges. Each edge carries a quantum number related to area, and each node carries a quantum number related to volume. The spin network is not embedded in a background space. It is space. The connections and quantum numbers of the spin network define the geometry of space at the most fundamental level. When spin networks evolve in time, they trace out structures called spin foams, which are the space-time analog of spin networks. A spin foam is a two-dimensional complex in which each face carries an area quantum number, and each edge carries a volume quantum number. The dynamics of loop quantum gravity, how the universe evolves from one state to another, is described by the amplitudes associated with spin foam transitions. The discreteness of space in loop quantum gravity has dramatic physical consequences. The most celebrated is the resolution of singularities. In classical general relativity, as we discussed, singularities are inevitable. The matter in a collapsing star is crushed to infinite density at the center of a black hole. The universe was compressed to infinite density at the Big Bang. But in loop quantum gravity, the discreteness of space prevents this from happening. You cannot compress matter below the Planck density because there is no space below the Planck volume. The quantum geometry creates an effective repulsive force at extreme densities that halts the collapse. This has been worked out most thoroughly in the cosmological context, leading to a scenario called loop quantum cosmology. In this picture, the Big Bang was not the beginning of the universe. It was a big bounce. Before our current expanding universe, there was a previous universe that was contracting. As it contracted and the density approached the Planck density, quantum gravitational effects became dominant and produced a repulsive force that reversed the contraction into the expansion we observe today. The singularity at the Big Bang is replaced by a smooth quantum transition, a bounce at the Planck density. The big bounce is a specific, concrete prediction of loop quantum gravity that differs sharply from the prediction of classical general relativity. Unfortunately, directly testing it is extraordinarily difficult, because the bounce occurred at conditions so extreme that almost all trace of it has been erased by the subsequent evolution of the universe. However, some researchers have suggested that subtle signatures of the bounce might survive in the cosmic microwave background radiation, the afterglow of the Big Bang, in the form of specific patterns in the temperature fluctuations or in the polarization of the radiation. Another dramatic prediction of loop quantum gravity concerns the fate of black holes. Carlo Rovelli and Francesca Vidotto proposed in 2014 that when matter collapses to form a black hole, it does not form a singularity. Instead, it collapses until it reaches the Planck density, at which point the quantum gravitational repulsion causes it to bounce. The collapsed matter forms a Planck star, an incredibly dense object at the Planck density that then begins to expand again. Because the bounce happens deep inside the black hole, where the gravitational time dilation is extreme, the process that takes a very short time for the collapsing matter appears to take an enormously long time from the perspective of an observer outside the black hole. From the outside, the black hole appears to be long-lived and nearly static. But from the inside, the matter bounces almost immediately and begins expanding outward. Eventually, according to this scenario, the expanding matter bursts out of the event horizon, and the black hole transforms into a white hole, a time-reversed black hole that ejects matter rather than absorbing it. This process might produce a characteristic burst of radiation that could, in principle, be observable. Some researchers have suggested that certain unexplained astrophysical signals, like fast radio bursts, might be the signatures of Planck stars bouncing. Loop quantum gravity, however, faces its own significant challenges. One of the most important is the continuum limit problem. We know that at large scales, space-time appears smooth and continuous, well described by general relativity. But loop quantum gravity describes space as a discrete spin network at the Planck scale. The theory must show that when you zoom out from the Planck scale, the discrete structure gives way to the smooth spacetime of general relativity. Proving this rigorously has been extremely difficult, and it remains one of the most important open problems in the field. Another challenge is that loop quantum gravity, unlike string theory, does not naturally include the particles and forces of the standard model. In string theory, all particles emerge from different vibrational modes of the string. In loop quantum gravity, the theory describes only the geometry of spacetime. Matter and the other forces must be added separately, and the way to do this is not uniquely determined. Some progress has been made in coupling the standard model to loop quantum gravity, but a fully unified picture has not yet emerged. The third major approach I want to discuss is causal set theory. This is a more minimalist approach that focuses on what might be the most fundamental structure of spacetime, its causal structure. The central postulate of causal set theory is that spacetime is fundamentally discrete, and that its fundamental structure is a set of discrete points, called elements, together with a partial order relation between them that represents causal relationships. The elements are sprinkled randomly, like grains of sand on a beach, at a density of approximately 1 element per Planck volume. The causal order tells you which elements can influence which other elements, which events are in the past of which other events. The idea was pioneered by Raphael Sorkin and collaborators in the 1980s. The philosophy is that the causal structure, the pattern of which events can causally influence which other events, is the most fundamental aspect of spacetime. Everything else, the dimension, the topology, the metric, the curvature, all of it should be recoverable from the causal structure, plus the information that the elements are discrete and randomly distributed at the Planck density. This might sound overly minimal, but the approach has produced a remarkable result. In the late 1990s, before the discovery of the accelerating expansion of the universe, Sorkin used causal set theory to estimate the cosmological constant. His argument was roughly this: the number of causal set elements in the observable universe is about 10 to the 240. The cosmological constant, which in this framework is related to a kind of fluctuation in the number of elements, should therefore be of order 1 over the square root of 10 to the 240, which is 1 over 10 to the 120, which is approximately 10 to the negative 120 in Planck units. This is remarkably close to the observed value. In a field where theoretical predictions of the cosmological constant are typically wrong by 120 orders of magnitude, getting a result within the right ballpark is an extraordinary achievement. It is one of the very few genuine predictions in quantum gravity, and it was made before the observational data confirmed it. However, causal set theory is still in the early stages of development compared to string theory and loop quantum gravity. The full quantum dynamics on causal sets remain an active area of research. Constructing a complete theory that reproduces both general relativity and quantum field theory in the appropriate limits is an ongoing challenge. The fourth approach I want to mention is the asymptotic safety program. This approach takes a radically different perspective from the others. Rather than replacing quantum field theory with something new at the Planck scale, it asks whether quantum field theory might actually work at the Planck scale after all, just in a non-perturbative way. The idea, originally proposed by Steven Weinberg in 1979, is that the apparent non-renormalizability of gravity might be an artifact of perturbation theory, the approximation technique used in most quantum field theory calculations. When you do perturbation theory, you expand your answers in powers of the coupling constant, which for gravity grows with energy. At the Planck energy, this expansion becomes useless because the coupling is of order 1. But this does not necessarily mean that the theory itself is sick. It might mean that the approximation technique is inappropriate. The asymptotic safety scenario proposes that the gravitational coupling constant, as you go to higher and higher energies, does not blow up to infinity, but instead approaches a finite value, a so-called ultraviolet fixed point. At this fixed point, the theory is well defined and makes predictions, even though perturbation theory cannot see this. Evidence for the existence of such a fixed point has been accumulating over the past 2 decades, primarily through a technique called the functional renormalization group. Numerous calculations have found what appears to be a viable ultraviolet fixed point for gravity, with a finite number of relevant parameters. If this is correct, then gravity might be a perfectly well-defined quantum field theory at all energies, and the Planck scale, while important, might not require fundamentally new physics. However, the evidence is not yet conclusive. The calculations involve significant technical approximations, and whether the fixed point survives in the full, exact theory is still debated. Connecting the asymptotic safety scenario to the specific predictions of particle physics and cosmology is an active area of research. There are several other approaches worth mentioning briefly, each offering a different perspective on Planck scale physics. Doubly special relativity, proposed by Giovanni Amelino Camiglia in 2002, modifies Einstein's special relativity to include the Planck energy as a second observer-independent scale, alongside the speed of light. In ordinary special relativity, all observers agree on the value of the speed of light, regardless of their relative motion. In doubly special relativity, all observers also agree on the value of the Planck energy. This leads to modifications of the energy-momentum relation at high energies, which could in principle be tested through observations of high-energy photons from distant astrophysical sources.